It's time to start a new repair series. You've seen one of these on my channel before. I've repaired a lot of these, and it's a power supply out of a PDP8. And as I say, I've repaired, I don't know, 30 or 40 of these over the years. They tend to have fairly common faults, had a few with some fairly unusual faults. This doesn't belong to me, it's been sent to me for repair. And from what the owner says, if he tries to increase the input voltage to drive the power supply beyond a certain relatively low voltage, then the fuse blows. I'm assuming he means this fuse because one end of it isn't connected. And this is a fairly common fault. I'll just, he sent it with wires tied up to protect them. We'll just get these off. Get this tape out of the way. Okay, so these aren't too bad to work on. They're a bit of a fiddle sometimes if you need to keep taking the PCB out. There are some large components on the underside of this. Before we get started, I'll just explain the general approach. I have explained in quite some detail how these supplies work, so if you want to go back and have a look at those videos if you're interested, by all means pause here and go and have a look. So this is the schematic for this supply. 3 main rails and a power monitor circuit built in to the unit, and this is the part we're most interested in to start with. This is where the issue is most likely to lie. So I've printed off this part enlarged, so that's this, and it is a switching supply, but it's not really the switch mode supply you'd be familiar with. There's no transformer as such. There is a big inductor, but this is a switching pulse width modulation control supply. This is really nothing more than a big Schmidt trigger with a few protection circuits built in. Now, I have seen comments online about you shouldn't ramp up these supplies slowly, you can damage them. It's actually not true in this case. It's perfectly safe to ramp the voltage going into this up as slowly as you want to. In fact, it's a very good way of testing it. So all we really have is this main pass transistor, this inductor, this diode and this capacitor. These form the heart of this particular supply. So the way that it works is we have raw DC coming in here. It comes through this resistor, we'll come back to that in a second, through the main switching device, the main pass transistor, and this is pulsed fully on or fully off, so that's what makes it efficient. It's not a linear supply as such, and when it's switched on, current is fed through the inductor and goes into this capacitor and out to the load. When the transistor turns off, the back EMF puts this diode into conduction, the current continues, and it continues feeding current out to the load, and it just switches back and forth. The point at which it switches, and hence the regulation, is controlled down here, and it's controlled by comparing the output with a reference voltage which is provided by this Zener diode, and as the voltage ramps up and down at this point, then the circuit will switch the main pass transistor on and off in a pulse width modulation style to control the amount of energy going through and hence the voltage. This resistor here is for overcurrent protection, so when the voltage across it increases sufficiently due to the increase in current flow, it will turn this transistor on, and this overrides the reference voltage and it forces the pass transistor to turn off, puts it into current limit mode. Now, of course, that only works if the pass transistor is actually functional. If it's short circuit, of course, then that won't work. So there's a second level of protection, which is down here, and then through this diode, if the voltage gets too high, then it will turn this device on. And what this does, it shorts the output through this diode to ground, and it also, through a very low value resistor, 0.1 ohms by the way, shorts the input incoming DC rail, and this causes the fuse, the main fuse, well not the main fuse, but the main fuse to blow in the supply, which is the fuse that's down here. So if we look at the overall schematic, we've got the DC coming in here, comes through that fuse, And then we've got these huge capacitors on the back side of that fuse, so they're effectively outside the fuse. So if the fuse blows, those capacitors are disconnected from the regulator, and that means that this device or the load doesn't have to discharge those capacitors. They are very big, beefy capacitors, quite high voltage, and trying to dump all that energy through a device would most likely destroy it. So the most common failure I've seen in these is this device. Sometimes the drivers will fail as well. Now and again we'll get a failure of the diode. I don't think this is short, simply because from what the owner says, he's able to ramp up the voltage before the current suddenly increases, so most likely it's the crowbar protection clamp kicking in. Could be something to do with the feedback, of course, but the easiest way to test this is to hook up a bench supply to the input. Safer than doing it on the mains because we can current limit it, and then slowly ramp up the voltage and see what happens. If we go into clamp mode and the crowbar kicks in, then we know where we're supposed to start looking. So we'll get that done. I'll get it hooked up, get the meter on, and then we'll see what happens when we try to feed power into this. Okay, well, I have the power coming in to this point. The meter is connected to the 5-volt output and everything is referenced to ground. So as we start to increase the voltage on the bench supply, then we should see the output voltage start to increase. This won't be switching, of course, because, well, in theory it won't, because we won't be getting to the switching threshold. But at some point, if it's working, the pass transistor should switch off, and then it should start to run in its regulation mode. But we'll see what happens. I suspect, judging by what the owner said, that it's just going to trigger the crowbar protection, but let's see what happens. So we'll start with the supply set to 1 volt. We'll switch that on. You can see the voltage starting to rise. Got the current limit set to 300 milliamps. It is going to respond fairly slowly because there's a fairly large capacitor on the output here, so that's what's charging up, and that's what we saw reduce the speed at which the voltage increased. So we'll increase the voltage, go to 2 volts. There is voltage drop, of course, because it is drawing some current. So nothing untoward yet, it's only drawing 7 milliamps, and we'll keep going up. So that's 3 volts. That's 4, 5, 6. So remember, this is on the output across the point that's being monitored by the crowbar protection. So nothing's happened yet. I'm going to start going up in tenths of a volt now. So 6.1, 2, okay, we're up to 7 volts going in, 6.3 coming out, so that's very close to the threshold if it is the crowbar that's causing it to suddenly go into shutdown mode. And there it's gone. It's we'll see if that's repeatable. So I got 7.5 volts on the input. We'll switch that back on. It's immediately gone back into shutdown, and we'll reduce the voltage a bit further. Start at 6.8, see what happens. So that's fine. We'll start to increase the voltage again. But the important thing here is we're at 6.4 volts on the output, and yet it's still trying to pass more current. This should now have switched off, and it's obviously still driving it. We'll just keep going up, see if the crowbar kicks in again. And yeah, sure enough it does. So what we can do now is just have a quick look to see if the circuit's actually trying to turn this device off. If it is trying to turn it off but it's staying switched on, then we know that there's likely a problem with this particular transistor. But we'll just monitor this first and see what we find. So before I start removing anything, and we'll have a bit of a poke around and see if we can figure out what may be going on. So I've currently got the supply set to about 5.5 volts. So the output that you'll see on the meter is just under 5 volts, so that's at this point. So what we can do now is check that this voltage is getting into the feedback loop. So we'll follow this chain down and we'll try looking at this point and see if that voltage is being dropped. It should of course be dropped through this arrangement here. So I believe, let's try to peer around the camera here. So that is that device. So one end should be ground. So we're looking at this resistor. This also acts as a temperature compensation device as well. So we've got ground at one end. Okay, and that appears to be the full voltage at the other end. So this device, it's labelled as 100 ohms. Seems to be open circuit, so we'll follow this through and see if this is actually trying to switch on or off and actually doing anything. I've got a feeling this is just essentially tracking whatever this is doing. Although I should still tell it to turn off. Okay, so we'll check this point. This is this point here. So it's going to check to see if this arrangement has been commanded to switch off. Okay, we'll start increasing the voltage and see what happens. Yeah, so it's just tracking up and down. It's not actually switching as it should do. So I've got a feeling there's something amiss down here somewhere. So what I'm going to do now, I'm actually going to take this device out, and that way we can just sometimes if this goes short, then it will cause some strange behaviour down through this path. So I'm going to take this out, but I suspect we've got an issue down here. So next step, we'll take out the main pass transistor. We'll stick it into the curve tracer just to make sure it's working. These aren't too difficult to get apart. There's just 6 screws and you can lift the board out. You do need to unplug the transformer when doing that, but we're not using that at the moment anyway. And then we can just unsolder and remove the pass transistor. So I'll get that taken out and then we'll get it into the curve tracer to see what we find. I've removed the device from the power supply. We've got it in the curve tracer here, so we'll try and switch this on. We've got the curve tracer set up, should give us a reasonable set of results with this device. So we'll switch it on. And as you can see, that is not right at all. Kind of reading like it's got a complete short. Very strange looking results. It is working to a certain extent, but then it kind of just collapses and stops working. So we'll put the intended replacement in here and you'll see what it should look like. Okay, so this is a new one. Exact same setup. We'll try and test this one. And as you can see, that looks much better. It's doing what it's supposed to, and it's acting like a transistor. So I'll get this one fitted to the supply. I don't think that's what the fault is. Like I said, if this was dead short, then the control circuit should still be trying to switch it off, and it's not. It's just tracking up and down with the output voltage. So I think the underlying fault, possibly what caused this device, or the one that we've just seen as faulty, I think that what's caused it to fail is probably the control loop not doing what it should. It is safe for us to put this device in and power up the supply using our test setup, because we are current limiting it, and this is a 30 amp device, so we're easily not going to damage it, but also the very large capacitors have been removed as well. So what we can do is fit the new device, power up our test system, and see what it does. I suspect it will do the same thing. Okay, this is the same setup we had before, so I'm going to try and power up the bench supply. Currently it's set to 5.4 volts. You can see the output is pretty much what it should be with this input, but I'm going to start increasing the input voltage and we'll see what happens. And it's done exactly the same thing. It's gone into over voltage trip, the crowbars come in, and it's not that surprising. I think from what we saw in the readings that we took, let's get the schematic. I think the problem is in this chain somewhere, because the voltage here, and hence the voltage going into the feedback, is exactly the same as the voltage here. There should be a voltage drop through this chain, and there's nothing whatsoever. So what I'm going to do is lift one end of this device and we'll measure this. If we don't get anywhere there, we'll try this one, and if we don't get any joy there, we'll try this. But yeah, if this wasn't working, then it would not be able to control the feedback. It wouldn't be switching this on and off, so that would make sense. So I'll lift one end of this, we'll see what this reads. Should read about 100 ohms. It is temperature compensation, so it does vary with temperature, but only by a small amount. It's not going to vary by kilo ohms. It's just a few ohms. So it should be somewhere close to 100 ohms. Okay, the unit's powered off, and I've unsoldered one end of this device, the top end. So the meter is now in resistance mode, and it's connected between ground, i.e. the bottom end of this resistor, and the other lead is connected to the top of the resistor. So we're just measuring this resistor. It should be around 100 ohms, and it's almost a mega. So that device is, to all intents and purposes, open circuit, which is why this is tracking with this. So I'm going to put a replacement 100 ohm resistor in, and I'm just going to tack it on the back of the board for now, just to see if that's the underlying cause. That would cause it to do what we were seeing. So with any luck, this is all that's wrong with it, just this resistor, and possibly it's damaged this device by having it turned fully on all the time. So I'll replace this and we'll see what we get. Okay, I've got a 100 ohm resistor tacked across the position where I've lifted this resistor. So in other words, this 100 ohm resistor is now tacked across this position, and the original only has one end connected. I've set up our test rig the same as we had it before. We're feeding voltage from the bench supply into this point. Everything's referenced to ground, and the multimeter is connected to the plus 5 volt out. So we'll see what happens this time. With any luck, the feedback circuit will start to kick in. I haven't actually measured this, but as I say, it's a new resistor, so it should work fine. We'll turn the supply on. It's currently set to 5.4 volts. In fact, what I'll do, I'll move the camera so you can see the supply. Okay, well, hopefully you can see the bench supply now. So as you can see, the bench supply is currently at 5.4 volts. It's still current limited to 300 milliamps, so it's not going to do any harm if this doesn't work. And the output is currently showing us 4.6 volts. So we'll try ramping up the input voltage. It's 5.4 volts, 6.4. That's going a bit high. And this might just need adjusting, by the way. I have been twiddling that pot around to see if it was faulty. So when I got what seemed to be an open circuit, I tried moving this pot to see if it was the pot itself that was wrong. So it will be out of adjustment, but hopefully this will start to regulate soon. So 6.4 volts, 7.4. Before going any higher, I'm going to see if we can adjust this down, because otherwise it will trip if it's too high. In theory, you shouldn't be able to adjust this high enough to trip, but I just want to see if this is actually working, and it actually is. So that's a good sign. That means it is now regulating. It wasn't doing that before. So we'll try turning the voltage up further. It's now 7.4, 8.4, and it hasn't tripped. Remember, it used to trip at about 7.5 volts input. 9.4, and the current's still about 80 milliamps going in. 10.4, 11, 12.4. So it does look like we have fixed this issue. What I'm going to do now, before we go any further, because for this circuit to work it does need those large capacitors on the input. So I'm going to reassemble this. I'm going to put the new resistor in properly, reassemble the power supply so it's in its case. We need it in the case really so that the fan works properly, although I did notice there's no foam in the bottom of the case, which is not a good idea because it stops any air blowing past this heatsink. I will advise the owner that there needs to be foam in the bottom of the power supply, otherwise you will get this issue. But as I said, I'll get this reassembled, and we'll give it a test, connect it to some electronic loads and see if the other rails work, and if we have actually properly fixed this. As you can see, I've reassembled the unit, and it's now time to give it a proper test. I haven't tested the 5 volt rail on load yet, and also I haven't tested the plus or minus 15 volt rails at all. I've resoldered the fuse into place, so hopefully that's not going to blow. I've noticed that the fan is really stiff, so I don't know if that will turn at all, and if it does it will probably make a lot of noise. Also, the foam is missing out at the bottom of this, so I can't put it on a long-term soak test at high power, even with the top plate on, because the foam's there to make sure we get plenty of airflow across the heatsink. So we'll give it a quick test. I will ramp it up to full power. I'll do that off camera once I finish the video. I don't want to bore you with sort of mundane testing. We just want to see here if it's fundamentally working. At the moment I've got the left hand electronic load connected to the minus 15 volt rail, the middle load is connected to the plus 15 volt rail, and the right hand load is connected to the 5 volt rail. The multimeter is connected to the power good output connector from the supply. I've got this supply connected to the bench mains supply, so I can power that up. I've got it configured for 240 volts, so it's a split primary winding on this transformer, so you can run it either 240 or 120. I will test it in the 120 volt mode as well before I send it back, but again I won't bore you with that. It's just rearranging the input and providing it with 120 volts rather than 240. So we'll get this powered up, and at the moment the loads are all set for constant current 1 amp, but they're not enabled, so we'll just see the kind of floating voltages. I want to make sure that the supply can regulate with no load. It's not going to trip just because there's no load connected to it. Okay, so I'll get this switched on, fingers crossed. Okay, as suspected, the fan is really noisy. I'm just going to turn this off and disconnect the fan so you can hopefully still hear what I'm saying. Good news is the rails do seem to be doing what we want them to. So I'll just unplug one of the leads from the fan and hopefully quieten it down a bit. Turn it back on. So as we can see, we're getting, although this says 15, it's actually minus 15. The load's connected backwards. These won't do negative voltages. And we've got a proper power good output showing. So we'll enable these. We should hear a bit more noise from the supply as we load it up. So I don't know if you can hear it or not. We're getting a bit of a whistle now from the supply, which is what we should have. It runs at about 10 kilohertz, so that's the tone that we're hearing. and finally the 5 volt. And they're all, as I say, on 1 amp, and it looks absolutely fine. We're drawing about 370 milliamps from the mains at about 220 volts, so again, efficiency looks fairly good. We're not making the supply struggle at all, so that is looking good. So I think the main culprit was just a failed resistor. So just 100 ohm resistor had gone open circuit. That had disabled the voltage control feedback for the 5 volt rail, and that in turn had damaged the pass transistor. So I will leave this running for a little while. We've got the extractors I mentioned in the past above this. I'll switch those on, leave it running for a while at probably put about 8 or 9 amps on the 5 volt, 3 or 4 amps on the minus 15 volt, and I'll leave the plus 15 at 1 amp, and hopefully that's this project finished. So not particularly exciting, but hopefully you found it of some interest. Like I said, I'll let the owner know before I send this back of the requirement to replace or repair the fan and fit the phone. I've been asked to indicate repair times and estimated costs on the projects where I show repairs. So for this one, total repair time was about 45 minutes. A great deal of that is setting up the camera and talking. It'd probably be a third of that if I was just doing it without doing any video or narration for it. Cost is the transistor and a resistor, so quite a low cost repair, and that's this now finished. It can go back to the owner and hopefully he can get it reinstalled in his machine.